Okay, we shall begin. I have not graded the exams yet. We'll get with my TAs later, meet up with them, TA and graders, and we'll grade through the exams. So just give us a little bit of time to get that done, and then we'll let you know how you did. Okay, well, we will continue our lecture on rejection sampling and take a look at the subject here. Okay, so we talked about this on Friday of last week, and we said rejection sampling. What it is it's a method for us to generate random values from some distribution, okay? And the time where we would use rejection sampling would be if we're trying to generate values and R does not already have a built-in random generator, okay? Because R already has a bunch of functions that we can use to generate random numbers. So if we don't have that, then the first method that we might turn to will be inverse CDF, or we might turn to use a convolution or something like that. But if in those cases, if we can't use inverse CDF because we can't figure out the CDF or we can't figure out the inverse of the CDF, we might turn to rejection sampling. And so the goal here, again, is we want to generate a random sample from some function f. And the requirement is you need to know the PDF. You need to know the PDF of f, okay? But perhaps the problem is that we don't know either the CDF or the inverse CDF, and we're not able to generate values directly from f. So what we will do is we will find a candidate distribution G, so just some other arbitrary PDF, okay? And the requirement is that the support of f, which is our target distribution, the distribution that we want, its support has to be inside the support of G, meaning that the function that we are able to sample from is theoretically able to generate any of the values that exist inside of f, okay? And another constraint is that there exists a finite constant m such that m times g of x is greater than or equal to f of x for all x, okay? So rejection sampling won't work in situations where, say, you have the t distribution versus the normal distribution, okay? If your target distribution is the t distribution, trying to generate samples from the normal distribution won't work, even though they technically have the same support. The t distribution has a support going from negative infinity to positive infinity. The normal distribution also has a support going from negative infinity to positive infinity, but you won't have a finite constant m such that m times g of x is going to be greater than or equal to f of x. If your target distribution f is the t distribution, it has much heavier tails than the normal distribution. So if you go out to, say, someplace far away, the ratio, if you do f divided by g, that ratio is going to be huge, and you would need to have a very, very big m, and eventually it's going to approach infinity. That m is going to approach infinity. And that's like in the extreme tails. Now, you might say, let's just realistically cut this off at, say, negative 10 and positive 10, and you might have a finite value there, but that finite value will still be quite big if you look at the ratio between what the normal distribution PDF is at 10 versus the t distribution, let's say t distribution with 2 degrees of freedom or something like that. Okay, that has a very heavy tail, and that ratio is going to be huge. Okay, so we need to find this constant m. Okay, the most efficient constant is going to be basically you want the smallest value of m that fulfills this condition and nothing anything larger, okay? So if you find the largest between f divided by g, okay, you don't want anything bigger. If you pick anything less than f over g, the max of f over g, then it will not satisfy this condition that m times g is going to be greater than or equal to f. Okay. So it needs to be at least this big, but to stay efficient, you don't want anything larger. Okay, and so the way it works is rejection sampling is you generate values from G, and then you calculate kind of this acceptance ratio, which is f of x divided by m times g of x. This gives you a value between 0 and 1. And then you will decide, using a random value from the uniform distribution, a random value between 0 and 1, should I accept this value or not? And if u ends up being less than this ratio, you will accept it. And if u ends up being greater than that, you will reject it. Okay? So you will accept your generated value x with probability r of x, according to this ratio. All right, and so we will take a look at an example and hopefully derive a tiny bit of intuition from it. So the example we are going to look at is the folded normal, and we will just look at the standard folded normal. Technically, the folded normal doesn't necessarily have to be centered at 0. You can have a folded normal centered somewhere else with a different standard deviation, and it just means you're taking the absolute value of whatever number gets generated, okay? In our case, we will just take the standard normal distribution and take the absolute value of it, and that's going to be the folded normal. And so basically, we're just taking the positive half of the normal distribution, and it's going to be twice as tall, okay? Because it still has to integrate to 1, so the PDF of the folded normal is 2 times the PDF of the standard normal, okay? And the support is going to be x greater than or equal to 0. And what we will use as our candidate distribution is we will just use an exponential distribution, which has this PDF. Now, this was an arbitrary choice. We could have used several other distributions, but this is a fairly simple one. And we are able to generate values from the exponential distribution using inverse CDF method. We just kind of take a random uniform and we take the log of it, and then we make it negative, right? And you take negative of the log of some random uniform value, and that's going to follow an exponential distribution. So we could generate values from the exponential, and we can use that to do rejection sampling with the folded normal. So the support of the exponential is compatible with this. The question is, what is the constant m that I should use? Okay, we want to find the smallest value, or we want to find the largest value between f divided by g. Okay, so here I have plotted the target distribution. The distribution we want is the folded normal, and it is twice as tall as the regular normal distribution, and this appears in red. And then the exponential distribution appears in orange. And if you were to integrate both of these things from 0 to infinity, both of these would have the same area. They would both have an area of 1. And just looking at it, they look like they're a comparable area, right? If you look at area under the red curve, it looks to be around the area under the orange curve, and they are, okay? And the fact that you have the same area means that if there's a region where the red line is above the orange line, then there has to be a region where the orange line is above the red line. Otherwise, you're going to have different areas, right? If both are kind of constrained to have the same exact area, same area of 1, and one function is taller than the other function in one spot, then that means there has to be another spot where it's shorter or the other function is taller. Okay, and so what we want to do is effectively we want to turn the distribution that we are able to generate from, that is the exponential, we want to multiply it by a constant so that m times g of x is going to be greater than f of x everywhere, okay? So basically I want to multiply the orange line by some constant so that the value of m times g of x is going to be bigger than f of x, the red line, everywhere, okay? So where do I do that? I'm going to find the value of where the red line, the ratio between the red line over the orange line is as high as possible. So we're going to do f divided by g of x. We're going to find the maximum of that value. Okay, so we're going to find this constant m, which is going to be f over g of x. And if we set it equal to, the most efficient choice of m is the max of f over g of x. So putting in the PDF for f, which is basically 2 times the standard normal, 2 over root 2 pi e to the negative x squared over 2, divided by the PDF of the exponential distribution. Exponential distribution, this PDF is e to the negative x, exponential with lambda equal to 1. That's what we have. And so, you know, thankfully for us, this is, we can combine these exponential terms. So now I have 2 over root 2 pi e to the negative x squared over 2 minus x, okay? So what is the maximum value of this? All right. So if you just kind of look at this and you think, okay, the maximum of e to the negative x squared over 2 minus x, right, it's e raised to a negative power. The largest value we're going to get is going to be at the minimum of x squared over 2 minus x. So if we say, okay, well, where's the minimum of this thing, okay? Well, x squared over 2 minus x, that's just a polynomial. We can do a tiny bit of calculus. Or, I mean, there's a few ways to do this. I didn't bother doing the calculus, right? You take the derivative, set it equal to 0, and you solve. And you're going to find that the minimum occurs where x is equal to 1. Okay, so if I plug in x equal to 1 into here, what is this value going to be? Okay. So the maximum occurs when x is equal to 1, and we would get 2 over root 2 pi e to the negative 1/2 minus 1. This is 2 over root 2 pi e to the 1/2. I get m something around 1.32. 1.32. Okay, and if I multiply the plot, okay, I guess I didn't draw this plot, but basically if I multiply the orange line by 1.32, it will raise it so that the red line is completely contained inside the curve. And there's a picture of this kind of right here. So when you multiply the orange line, the exponential curve, by 1.32, you're going to get this kind of this blue curve, and we can see that the red line is fully contained underneath the blue curve. Okay. So that's kind of the picture here. So if you look back at this one, here's the orange line. It's below the red line at some point, but if you multiply by 1.32, you're going to get this. Okay, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter C. C as in cat. C as in cat is our first view quiz answer. Okay, so here is just how the function will work. So here's just the algorithm. The constant that we're going to use is 1.32. The f is basically 2 times d norm, okay? That's 2 times the normal PDF, is the PDF of my folded normal, okay? And then here, g is the PDF of the exponential distribution, okay? E to the negative x. So just to kind of really illustrate that we're doing this, the ratio being f divided by m times g of x, I define, what is f and what is g, okay? So here I'm just going to say, let's generate 100,000 of these values, 10 to the 5. I'm going to generate values from the exponential distribution, so I'm going to ask for 100,000 values from the exponential distribution. These are my proposed values of x. These follow the exponential distribution. But I don't want to accept all of these. We're going to reject some of them. That's the point of rejection sampling. So we are going to create an acceptance ratio, R of x. And this is going to be different for every single value of x that I've generated. Some values of x will have high acceptance ratios, and some values of x will have low acceptance ratios. So that ratio is going to be f of the proposed x divided by m times g of the proposed x. And again, f is 2 times the normal distribution, it's PDF, and and g is the exponential PDF. So we do that. This gives me a bunch of ratios. I'm going to have 100,000 values in R of x, 100,000 ratios. I'm going to generate 100,000 random uniform values. 100,000 random uniform values. And then I do this comparison. I say, is u less than the ratio of x? Right? And this will give me a logical vector of true and false values. Some will be true, some will be false. And I will then subset my 100,000 values to just those that are true. So what I'm going to get here, accepted x, is going to be less than 100,000. It's going to be something around, I don't know, 70% of that. Okay, something around that. All right, is that okay? Just kind of the steps in code, what we've done. Okay, so this picture, what I want is it to give you a tiny bit of intuition here. So again, we generated values from the exponential distribution. Okay, so here is the histogram of the proposed x values. The proposed x values follow the exponential distribution. The histogram of proposed x values, and because I generated 100,000, we're gonna have very close alignment. Okay, I mean there's just a tiny bit of maybe where it's just a little bit different from the theoretic PDF, but the proposed values follow the exponential distribution. Okay, and that's what we see is values near 0 appear very frequently, values around 2 show up less frequently, and values around 6 show up very infrequently, okay? But what we want is our distribution, the final resulting distribution, to look like the folded normal, okay? So here is the PDF of the folded normal, okay? And this is going to run into a problem, right? The exponential distribution produces too many values around 0, and it doesn't produce enough values around 1, 1.5, okay? There's kind of a gap where the exponential distribution is too low, and then it starts producing way too many values around 2, 3, 4, okay, compared to the normal PDF, okay? So what we're going to do is we're going to either multiply the exponential by m, or we could scale down the red line by m. Right, so we either multiply, so I think what we're going to do is we're going to basically take this red line and divide by m, or we can think of it as taking the orange line and multiplying it by m. And so basically the resulting curve that we get is going to be the exponential follows this blue line, and then the folded normal PDF follows the red line. Okay, and now there's no region where the red line is taller than the blue line. Okay, and we found it by kind of taking that spot at x equal to 1, which is where the difference is the greatest, the ratio between the red and the orange is the greatest. When we take that, that's the spot, and so this is kind of where it aligns. We have They meet there, and everywhere else, there's a little bit of a difference there. Okay, so let's take a look at this very first interval here. So if we take a look at this bar here, and we can think of this bar as being centered at 0.05. Okay, so here's I think each bar has a width of 0.1. Okay, it goes from 0 to 0.1, the next bar goes from 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, 0.4 to 0.5. So this first bar goes from 0 to 0.1 It's centered at 0.05, okay? It's all of the values here aren't necessarily exactly equal to 0.05, but we can just kind of use 0.05 as like a representative value, okay? So think of 0.05 as this bar representing the values around 0.05. And we are generating, according to the exponential distribution, we're going to generate this value a lot, okay? It's the tallest bar here. Values around 0.05 get generated a lot, okay? But according to the folded normal, it's too many. We don't want all of these things, okay? We only want some of these. So what percentage should I accept? What percentage should I accept is basically the ratio between the height of the entire bar, which is the value of the blue line, okay, compared to the height of the red line. Okay, so if we do the height of the red line divided by the height of the blue line, we're going to get a ratio. Okay, this looks to be maybe something around 70%. I'm going to accept around 70% of values around 0.05. Does that kind of make sense here? If we focus in on this bar. So when we do the calculations, okay, when we look at the PDF of the folded normal, the PDF of the folded normal is 0.79689 at 0.05. So if I plug in 0.05 to the PDF of the folded normal, I get something around 0.8. Okay? And then when we look at the PDF of the exponential times m, so if we do m times the PDF of the exponential, I get 1.255. Right? So what's the ratio between f and m times the exponential? F at 0.05 divided by m times g at 0.05. Okay, it's actually less than 70%. It's only 63%. Okay, 63, 64%, 63.5%. Okay, so if I do this calculation, 2 times d norm 0.05 divided by 1.32 times d exponential at 0.05, I get about 63%. So this says, when you generate a value around 0.05, don't accept all of them, only accept around 63% of those. Okay, and how do we ensure that we only accept around 63% of those? We generate u, and we will only accept it if u is less than 63%, okay, or 0.63. And that's what we do. All right, so our exponential will produce values between 0 and 0.12 frequently, values around 0.05 very frequently. If our exponential produces a value of around 0.05, we only want to accept around 63% of them. How do we do this? We generate our unif. If that generated value from our unif is less than 0.635 or whatever the ratio is, we will accept it. Otherwise, we will reject it, which means sometimes we will generate 0.05. We get a u that's greater than 0.635. We get a u of 0.8. And we're going to reject that value. Okay, and then we just kind of repeat this over and over again. Okay, let's take a look at this location right here. So this is a bar spanning from 1.4 to 1.5. It would be centered at 1.45. And if we look at this, what's the ratio between the blue line and the red line? It's pretty close, okay? We're going to if we generate a value at 1.45, we're probably going to accept it, okay? We'll still reject some of it, but not too many, okay? So here we plug in 1.45 as kind of a representative value for this bar. Okay, and again, the distribution is continuous, so the probability of getting exactly 1.45 is 0, but we're going to choose the 1.45 as kind of a value that represents this bar. And the PDF of the exponential, the PDF of the folded normal is 0.2788, okay? So this is kind of the density of the folded normal distribution. If you look at the PDF of the exponential multiplied by that constant, 1.32, you get a value of 0.30963, okay? So this height is 0.30963, this height is 0.2788. And so what's the ratio between 0.2788 over 0.309963? You get something around 90%. Okay? So if you generate a value at 1.45, something around there, you will accept it with a probability of around 90%. So most of these values will get accepted. Right? If we were to calculate it for 1.0, we would accept 100% of them, right? So at 1.0, we would accept 100% of these values. So again, we generate a random value u from the uniform distribution. If it's less than 90%, we accept it, so we're going to accept it 90% of the time. If it's greater than 0.9, we will reject it. We're going to reject it 10% of the time. All right, let me go ahead and give you your second view quiz answer for today. Today's second view quiz answer is the letter E. E as an elephant. E as an elephant. All right, so here is a plot of a whole bunch of dots, okay? And the dots are generated according to the exponential distribution, which means we get more values around 0 and fewer values around 5 or 4 or 5, okay? If you look at values that got generated around 4, there's maybe only 3 of them, okay? If we look at values generated around 0, there's a whole bunch of these dots, okay? Values generated around 1.5, 1.45, there's some, okay? Their vertical location, so again, we're only generating values along the x-axis, okay? These are all the values that we're proposing. The vertical location represents what was the random u that we kind of generated, okay? If the random u was 1, it goes up to the blue line. If the random u was 0, it stays at the bottom. If the random u is 0.5, it's halfway between the bottom and the blue line, okay? So random values of u at 0 go down here. Random values of u at 1 show up at the blue line, and 0.5 would be somewhere halfway in between, okay? And so basically, if that random value of u ends up below the red line, which represents the PDF of our target distribution, we will accept it. And if the random value of u ends up being above the red line, then that means these are values that we rejected, okay? And so these values are randomly, uniformly distributed vertically, giving a sense of how often we accept versus reject. And I have an animation to illustrate this, okay? And so this is an animation that was created in R. And so I will cycle through just kind of the first few button clicks, okay? So here I am proposing values according to the exponential distribution, which is shown in blue. Okay? And what you will see is that values near the blue, or near 0, will be proposed more frequently, and values out here will get proposed less frequently. Okay? So this is, the first value I'm proposing is something around, 0.8, 0.9, I don't know, okay? And now I generate a random value u. Again, 1 represents it's up at the blue line, 0 represents it's going to be at the bottom at the x-axis, and we're getting something, this is probably like 0.4, okay, 40% of the way. So this is underneath the red line, so we're going to accept it, okay? So this is, so green means we've accepted it, and we're going to move on. And so this is going to show up as a black dot here, okay? Here's another value. We're proposing something like 0.1. What is the random value u that I generate? Looks like to be 0.9 or something. That's above the red line. We're going to reject it, okay? So that will not end up being part of our sample, okay? Here I propose the value 2, okay? And at this value, the random u I generate looks like 0.99 or something. We're going to reject this value. We don't accept it. Okay, here I generate a value maybe around 0.4 along the x-axis, okay? And the random value u I generate looks like 0.1, 0.05, I don't know, something very small. We're going to accept this value. This shows up in green. Okay, and we kind of just repeat this process. So here I generate a value 2, maybe 2.01, something very close to another value I proposed already. And this time the random U I generated is like 0.1, and so we're going to accept it. And that goes in as part of our sample. Okay, and then so I'm just going to click play, and you'll see this kind of process. And as you watch, you're going to see values over here get generated more often, and you'll see, you know, the vertical line ends about here infrequently, and when it does end about here, almost certainly it's going to get rejected, okay? And then, you know, if it'll get generated out here, you know, occasionally, and then sometimes it'll get accepted and sometimes it'll be rejected. But you'll see this vertical bar show up, you know, quite often over on the left-hand side. All right, so here, I don't know if it's going too fast, but it's kind of generating, proposing different x values, and every time it's just putting proposing a different location vertically, and if that vertical location ends up above the red line, we reject it, and if it ends up below the red line, we will accept it, okay? And so you can see most of the time, the black line stays kind of between 0 and 1, okay? And occasionally, right, it pops out over there. Very rarely you'll see it pop over to 3 or 4, okay? But it will, on occasion. Most of the time between 0 and 1, sometimes. So we were out there, got rejected. And again, it ended up at 3, got rejected. And so this is basically how the rejection sampler works, just probably a lot faster without the animation. But I don't know, I thought the animation is kind of fun to watch here. This is how I entertain myself. Making things. Okay, how long should I let this run? I think I had to generate like a couple hundred points here. Okay, I guess that was it. So it looped around. All right. Wait, stop. Okay, so this is kind of the resulting thing here, and so we can see, yeah, how often did it generate a value or propose a value greater than 3? And it proposed a value maybe only 3 times, 3, 3.9, 3 point something, you know. It only proposed that value out there a few times, and when it did, all of them got rejected, okay? How often did it propose values greater than 2? Sometimes, not very often, and it only accepted a few of these, right? And overall, you know, if we look at, you know, what proportion of values are less than 1, what proportion of values are less than 2, what proportion of values are less than 3, you know, this is going to fit kind of the normal distribution properties quite closely. So here, I just said, here we're getting some empirical estimates here. I said, how often did I propose a value less than 0.1? Okay, so after 100,000 values, I proposed values less than 0.1 between 0 and 0.1, 9,596 times. Compare that to how many did I accept? I accepted around 6,003 of them. So the ratio of how many I accepted is 0.6255. Okay, compare that to, according to this, the theoretic ratio is around 63.5%, and empirically I accepted around 62.5%. Okay, how many values did I propose between 1.4 and 1.5? Okay, I proposed 2,328. Of those, how many did I accept? I accepted 2,107. And that's an acceptance ratio of around 90.5%. 90.5%, which agrees quite closely to the theoretic ratio that I should accept for values around 1.45. Okay, and just overall, how many did I propose versus how many did I accept? Okay, I proposed 100,000 values and I accepted around 75% of them, 75.5%. Okay, and again, the proportion that I accept is 1 over m. So m is 1.32. If you do 1 over m, you're going to get something around 75%. Right? Here's just a slightly more mathematically kind of rigorous approach, rather than just showing you some bars and coloring them in and saying this is approximately how many we would accept. Okay? What we need to show is that even though we're using this function g to propose random values of x, if we only accept some of these values, then the resulting distribution is going to be equal to f. Okay? So what we want to show is that the probability of getting some value x, given the fact that x is accepted, is equal to the desired PDF, target PDF. Okay? And so, so we can use Bayes' rule to do this, and this denominator in Bayes' rule can be found just by kind of integrating the numerator across all possible values of x. So we're going to say, what's the probability that x is, so the probability of getting a particular value of x, which is basically your PDF, the probability of getting your particular value of x, given the fact that x is accepted, can be found using Bayes' rules by saying, first let's find out what's the probability that x is going to be accepted if you've generated x, multiply that by the probability of generating that x, and divide that by the total probability of all x getting accepted. So the probability that x is going to be accepted for some generated value is going to be the probability that u is less than or equal to r of x, okay? Which is really just the r of x, okay? What's the probability that u is less than or equal to r of x? That's just r of x, okay? Multiplied by the probability of generating that x, that's going to come from g of x, okay? And then, what's the probability that x is accepted? Well, we would integrate the numerator across all possible values of x. So this part, what is r of x? That ratio is found by doing f of x divided by m times g of x. Okay? We're going to multiply that by the probability of generating x, which comes from g of x. We're generating x from the g distribution. Okay? So my numerator is going to become f of x over m. Okay? What is this denominator going to become equal to? All right? Well, when we integrate this, okay, well, the g of x's will cancel, and the integral of f of x is going to be 1. Okay? So this part is going to integrate to 1. This is just a constant, so we have 1 over m here. And this part, and this part cancel. So in the denominator, we're going to have 1 over m. In the numerator, we have f of x over m, because the g of x is canceled. And thus you have f of x over m divided by 1 over m, you're just going to get f of x, right? And that's to say that the probability of the PDF of x, basically the probability of getting this particular value of x, given that we've accepted it, is going to follow the target distribution that we want. So that's good. That's good news. That's exactly what we want, okay? Oh, I guess we're going to finish early today. That's fine. Okay. Rejection sampling looks and feels a lot like importance sampling. In both of these cases, we're kind of generating values from some other distribution, but to kind of get an answer for something that for a distribution that we're not able to do. Okay. They are similar, but they are different, and unfortunately, the names may just make it even more confusing, okay? So again, both scenarios, we're dealing with the problem of not being able to generate values directly from some distribution f, and both problems, or both of these methods say the solution is to just use a function that you are able to generate values from g, okay? And we use some kind of ratio f over g or f over m times g, okay? The key difference is this. With rejection sampling, the goal is to generate a sample. You want actually the values that you're going to use, right? You want to know what values can I use if I want to sample from this target distribution f, okay? Whereas importance sampling, you actually don't care about the values you've generated. Importance sampling is just a method to get an estimate for some integral, right? Or some function that we want often in the context of Bayesian statistics, but you're trying to estimate some value, some expected value of a function, and so you're going to just take all the values that get generated by G, and you just weight some of them. You say these ones are more important, these ones are less important, but we're going to accept all of these values of G. That's not going to work for rejection sampling because the goal of rejection sampling is to actually get the sample of values. These values I'm going to use, okay? You want to actually have values that came from this distribution. So G is generating a whole bunch of these values. You're going to accept some of them. You're going to reject some of them, okay? So rejection sampling does throw away values that don't meet the acceptance criteria, whereas importance sampling doesn't throw anything away. And importance sampling just weights some of them to be more important or less important, okay? And so personally, this is not, personally, I think importance sampling is not a good name. I think we should call it something like weighted Monte Carlo integration. I think that makes a little bit more sense because important sampling sounds like it's a method for generating a sample, but it's not used for generating a sample. But that's the name it has, and that's the name that exists in the literature, and so that's what it's called. But it's not a sampling method. But rejection sampling is. Okay. All right. Last view quiz answer today is the letter D. D as in dog is our last view quiz answer. Okay, and I'll just let you guys go a few minutes early today. So have a good day. We will see you guys on Friday.